Proper grounding is essential for electrical equipment, including pull lifts, according to the National Electrical Code, or NEC. Grounding creates a safe path for electrical current in the event of a fault, minimizing the risk of shock or fire. The NEC mandates that exposed non-current carrying metal parts of electrical equipment be grounded. This includes the metal frames, supports, and other non-current carrying components of pull lifts. The preferred method for grounding pull lifts is through a ground stud located in the in-ground socket. This ground stud must be connected to a suitable grounding electrode system, adhering to NEC standards. The in-ground socket should be designed to accommodate a ground stud. The stud must be constructed from a corrosion-resistant material, such as stainless steel, copper, or copper-plated steel. The ground stud must be securely anchored within the socket and connected to the pull lift frame using a corrosion-resistant bolt or screw. The grounding electrode system for the pull lift must comply with NEC requirements. It may consist of the following elements. Firstly, a bare copper conductor with a minimum size of number 8 AWG buried at least 8 feet below grade. Secondly, a metal underground water pipe. Thirdly, a metal building frame. Fourthly, a rod or pipe electrode driven into the earth. While the NEC provides general grounding guidelines, checking local, state, or municipal codes for additional or specific requirements is crucial. These codes may impose stricter grounding regulations for specific areas or environments. Regularly inspect the grounding connections of the pull lift to ensure they are secure and free from corrosion. Any damaged or loose connections should be repaired or replaced promptly. Remember that this information serves as general guidance only. Consulting with a qualified electrician is recommended for specific grounding requirements and to ensure compliance with all applicable codes and regulations. To elaborate on grounding electrode systems, it's helpful to understand their purpose and construction in more detail. The goal of a grounding electrode system is to provide a low impedance path to earth, ensuring that fault currents can safely dissipate, tripping circuit breakers or ground fault circuit interrupters, also known as GFCIs, and preventing dangerous voltage build-up on metal surfaces. The bare copper conductor, buried at least 8 feet below grade and no smaller than number 8 AWG, serves as a direct connection to the earth. Its size and burial depth are specified to ensure adequate contact with the soil, providing a reliable path for fault current. A metal underground water pipe can be used as a grounding electrode, but it must meet certain criteria. The pipe must be in direct contact with the earth for at least 10 feet, and it must be electrically continuous. It's essential to verify that the water pipe is indeed suitable for grounding, as some newer pipes may be made of non-conductive materials like plastic, which cannot be used for grounding purposes. A metal building frame, if adequately grounded, can also serve as a grounding electrode. The building frame must be electrically continuous and connected to the earth through a grounding electrode system. This is typically found in larger buildings with steel or metal framing. Rod or pipe electrodes are common grounding electrodes, particularly in residential and commercial applications. These electrodes are typically made of copper or galvanized steel and are driven into the earth to a specified depth, usually 8 feet or more. Multiple rod or pipe electrodes may be required to achieve the desired grounding resistance, as specified by the NEC. The NEC specifies the maximum allowable resistance to ground for grounding electrode systems. This resistance is typically 25 ohms or less. If the resistance exceeds this value, additional grounding electrodes may be required to reduce the resistance to an acceptable level. Ground fault circuit interrupters, also known as GFCIs, are crucial safety devices used in conjunction with grounding systems. GFCIs are designed to detect even small imbalances in current flow, indicating a ground fault. When a ground fault is detected, the GFCI quickly trips the circuit, interrupting the flow of electricity and preventing electrical shock. GFCIs are commonly required in areas where water is present, such as bathrooms, kitchens, and outdoor locations, including pool areas. The NEC has specific requirements for the placement of GFCIs in pool areas to protect swimmers and other individuals from electrical hazards. Equipotential bonding is another important safety measure used in pool areas to minimize the risk of electrical shock. equipotential bonding involves connecting all metal parts in and around the pool, such as the pool lift, the pool deck, and any metal fences or railings, to a common bonding grid. This bonding grid helps to equalize the electrical potential in the pool area, reducing the voltage difference between different metal parts. By minimizing the voltage difference, the risk of electric shock is significantly reduced. The NEC specifies the requirements for equipotential bonding in pool areas, including the size and type of bonding conductors and the methods for connecting the various metal parts to the bonding grid. Regular inspections and maintenance are essential to ensure the effectiveness of the grounding and bonding systems in pool areas. Grounding connections should be checked for corrosion, looseness, and damage. Bonding conductors should be inspected to ensure they are intact and properly connected. CFCIs should be tested regularly to verify they are functioning correctly. Any deficiencies or problems should be addressed promptly to maintain the safety of the pool area. In addition to the NEC and local codes, other standards and regulations may apply to pool lifts and their grounding systems. The Americans with Disabilities Act, or ADA, sets accessibility standards for swimming pools, including requirements for pool lifts. These standards may include specific requirements for the electrical safety and grounding of pool lifts. Manufacturers of pool lifts typically provide detailed instructions for the proper installation and grounding of their equipment. These instructions should be followed carefully to ensure the safe and reliable operation of the pool lift. It is important to note that electrical work should only be performed by qualified electricians who are familiar with the NEC local codes and other applicable standards. Improper electrical work can be dangerous and may result in electrical shock, fire, or other hazards. When selecting an electrician, it is important to choose one who is licensed, insured, and experienced in pool electrical systems. The electrician should be able to provide references and demonstrate a thorough understanding of the applicable codes and standards. In summary, proper grounding is essential for the safety of pool lifts and the individuals who use them. The NEC provides comprehensive requirements for grounding electrical equipment, including pool lifts. Local codes may have additional requirements that must be followed. Regular inspections and maintenance are necessary to ensure the effectiveness of the grounding system. Consulting with a qualified electrician is recommended to ensure compliance with all applicable codes and regulations. To further clarify grounding concepts, it's helpful to understand the difference between grounding and bonding. Grounding, as discussed earlier, provides a path for fault current to flow back to the source, tripping a circuit breaker or GFCI. Bonding, on the other hand, connects metal parts together to equalize their electrical potential. While grounding protects against electrical shock by providing a low impedance path for fault current, bonding protects against electrical shock by minimizing the voltage difference between different metal parts. Both grounding and bonding are essential for electrical safety, particularly in areas where water is present. The NEC addresses both grounding and bonding requirements in detail, providing specific guidelines for the size and type of conductors, the methods for making connections, and the locations where grounding and bonding are required. Understanding the NEC requirements for grounding and bonding can be challenging, even for experienced electricians. The code is complex and constantly evolving, with new revisions and updates being released every 3 years. It is important for electricians to stay up to date with the latest NEC requirements and to seek clarification from code officials or other experts when needed. Continuing education courses and professional development opportunities can help electricians maintain their knowledge and skills in the area of electrical safety. In addition to the technical aspects of grounding and bonding, it is also important to consider the human factors involved. Electrical safety is not just about following codes and regulations, it is also about creating a culture of safety and promoting awareness among all individuals who may be exposed to electrical hazards. Training and education programs can help individuals understand the risks associated with electricity and how to protect themselves from electrical shock. These programs should cover topics such as the proper use of electrical equipment, the importance of grounding and bonding, and the procedures to follow in the event of an electrical emergency. Safety signage and labeling can also help to raise awareness and prevent accidents. Warning signs should be posted in areas where electrical hazards exist, such as near electrical panels and equipment. Labels should be used to identify the voltage and amperage of electrical circuits and equipment. Regular safety audits and inspections can help to identify potential hazards and ensure that safety procedures are being followed. These audits should be conducted by qualified personnel who are familiar with the applicable codes and standards. Finally, it is important to remember that electrical safety is a shared responsibility. Everyone has a role to play in preventing electrical accidents and ensuring a safe environment for themselves and others. By following safe work practices, using electrical equipment properly, and reporting any potential hazards, individuals can help to create a culture of safety and prevent electrical injuries and fatalities. Considering the specific application of pull lifts, it's vital to ensure that all electrical components are rated for wet locations and are protected from corrosion. Pull chemicals such as chlorine and bromine can be highly corrosive and can damage electrical equipment if it is not properly protected. Electrical enclosures should be made of corrosion-resistant materials such as stainless steel or fiberglass and should be sealed to prevent water from entering. Wiring and connectors should also be rated for wet locations and should be protected from corrosion. It is also important to ensure that the pull lift is properly installed and maintained according to the manufacturer's instructions. Improper installation or maintenance can create electrical hazards and can reduce the lifespan of the equipment. Pull lifts should be inspected regularly for signs of wear and tear, corrosion, and damage. Any problems should be addressed promptly to prevent electrical accidents. In addition to the grounding and bonding requirements, the NEC also has specific requirements for the wiring methods used in pull areas. Wiring must be installed in conduit or other approved raceway to protect it from physical damage and corrosion. The type of conduit or raceway used must be suitable for wet locations and must be made of corrosion-resistant materials. Wiring must also be properly sized for the load it will carry to prevent overheating and fire hazards. The NEC provides tables and formulas for calculating the proper wire size for different applications. It is important to consult these tables and formulas to ensure that the wiring is properly sized. Overcurrent protection devices, such as circuit breakers and fuses, are essential for protecting electrical circuits from overloads and short circuits. These devices are designed to trip and interrupt the flow of electricity when the current exceeds the safe level. The NEC specifies the type and size of overcurrent protection devices that must be used in different applications. It is important to use the correct overcurrent protection devices to prevent electrical fires and equipment damage. Surge protection devices, also known as transient voltage surge suppressors, or TVSSs, are used to protect electrical equipment from voltage surges caused by lightning strikes, power outages, and other events. Voltage surges can damage sensitive electronic equipment, such as pull lift controls, and can cause them to fail. Surge protection devices divert the excess voltage to ground, protecting the equipment from damage. The NEC recommends the use of surge protection devices in areas where voltage surges are common. Finally, it is important to remember that electrical codes and standards are constantly evolving. It is the responsibility of electrical contractors and installers to stay up to date with the latest codes and standards and to ensure that all electrical work is performed in accordance with these requirements. Failure to comply with electrical codes and standards can result in fines, penalties, and legal liability. It can also create unsafe conditions that can lead to electrical accidents and injuries. By following the proper grounding and bonding procedures, using the correct wiring methods, and staying up to date with the latest codes and standards, you can help to ensure the electrical safety of pull lifts and the individuals who use them. This commitment to safety will protect lives and prevent electrical accidents.